Okay, so in the previous class, we had this transfer function of 1 over tau s plus 1, and we replaced s with the what j omega or y omega, and we plot the body for that, and we saw that it's a low pass filter like this, right? This is amplitude, and this is the phase, right? And this was the phase for the, and we named it as a low pass filter. Low pass filter, okay, because only passing the low frequencies, as you can see here, because this is logarithm log, so when the output is equal to input, they have the same amplitude, so log of 1 is 0. And then after that, for high frequencies, is being filtered out. Okay. Now let me go to the next for the first order system I was talking about. Another first order system that we're gonna analyze today for the body plot is S in S plus 1. So again, what we're gonna do, I'm gonna say is I omega or J omega and I omega plus 1 are replacing S. So the A, which is 20 log of this, the amplitude of this number, as I told you, is omega square over y square plus 1. Now, if the omega is much smaller than 1, so you say A gonna be 20 log of, okay, if omega is smaller than 1, let me put a number. Omega, say it is 0.1. It's much smaller than 1. So you're gonna write this as this, guys. Omega squared over 1, because 1 is much smaller than, because omega squared, if that's the number, gonna be this. So it's gonna be 220 log of omega. That's right. So by giving the number, for example, 20 log of this number, 0.01. So gonna be minus 20. Here we go. See what I'm saying? Yes. So if I say omega is 1, obviously you're gonna get the cut off the frequency. It's gonna be 20 log of 1 over 2, which is ballpark minus 3, which is our cutoff frequency. That's right. Cutoff frequency as I defined in the previous class for the low pass filter. And if I say is omega is much greater than 1, so your A gonna be 20 log of, so say, let me say omega is 100. Okay, so we're gonna say, because omega is greater than 1, I'm gonna say bye to 1. So 20 log of to 1, because it's gonna be like this. See, omega square over omega square. This is 1. So 20 log of 1 is gonna be 0. Simple like that. So if you are done, I will do it here. So if I want to plot it in the body excitation frequency for the first order system, here is 10 to the power of minus 1 for this, which is 0.1. 10 to the power of 0, 10 to the power of 2, 10 to the power of 3. So here's 2 and here is 1. 0. Oh, sorry guys, I made a mistake. Ten to the power of 1, 10 to the power of 1, 10 to the power of 2. Okay, at omega small number, it is minus 20. 1, 2, here. See here? Suppose this is, let me scale it because I don't want to do that. Suppose here is, oh, suppose here is small number, that's right. 10 to the power of minus 1, 10 to 1, and 100. So it's minus 20, it's here. Okay, here. Then at 1 is cutoff frequency, minus 3, here. Then at 100 is 0. So it's gonna be, here we are. So what's the name of this, guys? This is what? High pass filter. In the low pass filter, we are filtering out the high frequencies. In the low pass filter, you are filtering out what? The low frequency. That's right, exactly the reverse. So for the higher frequency, your output exactly in amplitude wise is equal to the input. So that's why is log of that is 0. Is log of 1. So this is high pass filter. High pass filter. Because passing the high frequency and filtering out the low frequency. See what I'm saying? Yes? So can I go to the next page? So for the phi, for the phase angle that I'm gonna do the MATLAB today after finishing the old topics. So again, this is omega excitation frequency. So the phase angle gonna be phase angle of, because I have the 1 0 here and 1 pole. Remember, for the low pass filter, you had only 1 pole, right? Real, imaginary. The only pole of the low pass filter is here, 1 minus tau s. But for high pass filter, you have a 0. See, you have a, where is that? You have a 0 at origin and a pole for here, say, as minus 1 here. That's the difference between them, right? So the phase angle of this, based on whatever I taught you previously, is the phase of the numerator minus phase of the denominator. Phase of the numerator minus phase of denominator. Obviously, we are replacing with I omega or j omega. They are the same. Obviously, this I omega can be written as this. Real part is 0. That's right. So, if I show it here, guys, look at here. Real, imaginary. This number, if I show it here, gonna be real part is 0, imaginary part is omega. Is this point. So what's the phase angle of this? What's the phase angle of this, guys? This part. Look at here. Or tangent inverse of omega over 0. What is tangent? What is omega over 0? What? Omega over 0 is 0? What is omega over 0, guys? What is 2 divided by 0? Means, mathematically, yes. So tangent inverse of infinity. How much is that from high school? Guys, which angle gives you infinity? Which angle tangent gives you infinity? Do you remember unit? Yes. Side here is cosine. Exactly. So it's 90 degree. What do you mean by a large number? A huge large number. 90. Minus tangent inverse of omega divided by 1. Imaginary part divided by real part. So the phase angle of the high pass filter is 90 degree minus tangent inverse of omega. So I'm going to plot it. Phi. At very low number, very small number, tangent of which tangent is low number? This is going to be 0. That's right. So it's going to be 90 degree. See here. Okay. It's going to be plus 90. Okay. This point. At very low number. At cutoff frequency, 90 minus tangent inverse of 1. Which angle gives you, which tangent of which angle gives you 1? These are high school, guys. 45, that's right. So it's gonna be 45. So say here is 10, 0, 10, 1, 10, 2. Okay, so here is say 45. So this is this number. Okay, at omega 1. At omega 100, gonna be 90 minus tangent inverse of 100. Which angles gives you a huge number, say even 1000? Which angle? 90. Gonna be 0. Here we go. So it's gonna be like this. Let's take this. It's gonna be like this. Here's plus 45. Meaning that for the high pass filter, they are in the same phase for high frequencies. But for the low frequency, you have the phase difference between the input and output. Understand, everyone? Yes? Everybody? So in phase, it shows that, look at here, guys. I want to plot it in the MATLAB, okay? Just bear with me. So suppose this is, because it's a frequency. This is input, that's right, as we did in the previous class. For high frequency, they have no phase difference. So the output gonna be like as the input like this. Okay, for high frequency. For low frequency, it's gonna be like this, guys. They have the phase difference, that's right. Actually, let me replot it. It's gonna be like this. See? the phase difference between them. See, between the maximum of those. Okay, so this is for low frequency. The blue one is for the low. I'm going to show in the MATLAB assignment. Low frequency. And the red line is for high frequency. Yep. Well, you have lots of noise, man. You have to put filter. Can you fix your voice? Yeah. Okay. Can I continue? Okay. Okay. So I will go to the MATLAB and I'm gonna plot it for the high pass filter. Now let me say output over input is this S. What's the name of S I taught you a million times by Laplace transform? What's the name of that? Which function gives you S? It's Laplace. D over dt means what is the name of this in the elementary school? Yes, derivative or decontroller. Decontroller. So it's I omega. I just want to plot its body diagram. So it's A gonna be 20 log of omega because its amplitude gonna be root square of this. We don't need to write that. So omega. If omega is very smaller than 1, or say give me a number 0.1, so A gonna be 20 log of 0.1, gonna be minus 20. At 1, A gonna be 20 log of 1, gonna be 0, exact 0. See here, we don't have that cutoff frequency here. Exact 0, not minus 3. Say a large number, 10 to the power of 2, A gonna be 20 log of 10 to the power of 2, gonna be how much? Let me put first this 10. Gonna be how much? Gonna be 20. Here we go. So if I plot the body omega, here is 10 to the power of minus 1, 10 to the power of 1, 0, 1, 10 to the power of 2. So it's interesting that versus omega, if here is A, at 0.1 is how much? Minus 20. Here is this point. At 1 is 0, this point. At 10, let me fix this. At 10, here is how much? 20. There we go. So you see, just despite the low pass filter and high pass filter, it is what? Straight line. Your decontroller is a straight line. This is interesting. So the phase of that, because this is only numerator, gonna be the phase of I omega, or phase of I omega plus 0, real part is 0. As we did previously, is 90 degree. So if I continue like this, omega, okay, because real part is 0, because it is tangent inverse of omega over 0, which is infinity, which is 90. So it is what? 90. Here we go. This is phi. Straight line. Despite a low pass filter and high pass filter, it is a straight line. See what I'm saying? Guys? Yes? So now, because I taught you the Laplace transform, can I go to the next page? Please let me know. Now let me say, let's say x over y is 1 over s this time. What is this? I told you? Yes, integrator or I controller. I'm exposing that to frequency response to see how it behaves. I'm gonna say close I omega. So it's A gonna be 20 log of 1 over omega. Or you can write as this 20 log of omega minus 1. I'm bringing it to the numerator. That's right, from algebra. So let me say omega is 0.1. So it's A gonna be 20 log 0.1 minus 1. That's right. How much is this, guys? How much is this? How much is this? Total, this gonna be 10. So this gonna be 20, exactly. Now if I say omega is 1, A gonna be 20 log of 1 to the power of minus 1. It's gonna be 0. Doesn't matter. If I say omega is 10, so A gonna be 20 log of 10 to the power of minus 1, gonna be minus 20. So I want to plot it here on the previous page. Why? Because I want to compare. At omega 0.1 is 20. Here we go. At 1 is 0. Oh my god. Here we go. At 10 is minus 20. See? This is just symmetry respect to axis y, right? So this is for I term. This is for D term, body plot. I'm just comparing. So the phase angle of that, because gonna be phase angle of number 1, numerator, minus phase angle of I omega. You can write number 1 as this 1 plus 0 omega minus I omega. So gonna be tangent inverse of 0, this, minus tangent inverse of omega over 0, which is infinity. This is gonna be 0, as we did this million times, minus 90. Here we go. So let me plot it, give you time to plot here. So comparing with this is gonna be minus degree. This is for I term, this is for D term. Understand, everyone? Yes? Great. Let me go to the Simulink and MATLAB to visualize what we learned. Until it comes up, you can write down here this. Here? No. Let me stop it because. Okay, guys. Let me open the ME530. Oh, body first. Okay. Because I have it, and I just don't want to kill your time. I just have to change the transfer function. Open loop transfer function, obviously. Okay, so before it comes up, I have to do something here, guys. Remember that because I have to modify the open loop transfer function. So remember that for the low pass filter that we had this, say S plus 1. So we know that the open loop transfer function is 1 over S. But for high pass filter, like as S or S plus 1, you have to find open loop transfer function 1 plus G from here. So S 1 plus G, G S plus 1. That's right. So S plus SG gonna be GS plus what? GS plus G. Right? Yes, guys? Huh? So SG, SG. So your open loop transfer function gonna be S. See what I'm saying? Let us examine this, see if this works or not. So for high pass filter, gonna be when you go to Simulink, let us examine that. So what I'm gonna do, I'm gonna copy this new to here, and I'm gonna make all of them here. Okay. I don't want to compare this with this. Okay. And 3, because I have 2 of those. Okay, I have to change this. So your open loop transfer function here gonna be S10, and here you have to put this large small number, this, because this is gonna multiply by S, means 0. See? Now this is your open loop transfer function for high pass filter. And I'm gonna delete this and copy paste here and put here. Here we go. See what I have done, guys? So because this is S and this is 1, this is multiplied, S multiplied by a small number means 0 and 1. So this is S. So now let me try amplitude. So phase, okay, for high pass filter. High pass filter means for low frequency. Okay, let me first cut it from here. I don't want to compare it first. For low frequency, based on the graph, for low frequency, the output has lower amplitude than input. Okay, so let me run it. And first, body high pass plus D plus I. Okay. So being said, come on. Being said, and I have to increase it to 30, and run it for low frequency. Okay. This is input to the system, okay? And this is the output of the system. See? We have much lower what? Amplitude. And you saw that the phase, as I plotted, where's the phase? We have lots, so for low frequency, we have lots of phase difference. Do you see that? Look at this maximum here. Look at this maximum here. They have lots of phase difference. So, but if I increase the frequency to, I don't know, 10 or say 100, they must be equal. Okay. Now I'm gonna connect this to this. Here we go. Because this is high pass filter, that's right. Oops. This is too much. That's right. It was lots of noise. Here we go. See, now they are much closer. Do you see that, respect to this? Okay, for high frequency. Even this is, I have a message here for you. Let me put that 1. Here we go. Do you see? They are closer, okay, to the amplitude, respect to this. See what I'm saying? So even that I can reduce this to 5. Oh, not this. To, I don't know, frequency of 2 or 3. A little higher. 10 times of this, that's right. This was 0.3. Here we go. Now they are much closer to the amplitude. See what I'm saying? Okay. So this is for that. And you see that if I plot the error signal of this high frequency versus low frequency, here we go. This is the error signal of the low frequency for high-pass filter. This is frequency of the this is frequency of the high frequency. This is the error signal of the high frequency. It's decreasing. See what I'm saying? Okay. That's it. So now you know it. But for now, let me go to this. Let me close this. No. Script CLC, clear all, close all. So okay, after having that, I want to plot body of derivative, meaning S, as we did together. That's right. So num is 1 and 0. Oops. 1 and 0, and then is closed loop transfer function. Here is closed loop transfer function for S. I mean this, guys. This. I want to plot this for S derivative. So then is, let me try this one, okay? Bear with me. Figure 1, body num then, and grid. Derivative integrator. Body. Let's see what happens. Oh, there's a typo here. Here we go, as we plotted previously. Okay. The slope of 20 over decade, and it's just plus 90. Do you see that? Yes? And to be compared with that, I'm gonna plot the integrator. Gonna be 0 and 1, 0 and 1, then gonna be 1 and 0, the integrator. Okay, body plot of integrator int 1 over S. So what I'm gonna do, I'm gonna say hold on, because I want to compare with this. I'm going to share this with you. Okay. num1. Here we go. Okay. See, they are totally changed. Here we go. See guys, minus 20 degree, minus 90, as we did previously in the class. Okay. It started from 10 to the power of 0, 10, 1. Okay. We started from 10 to the power of minus 1. That's why they have a different or plotting things. Okay. See what I'm saying? So as homework, try to plot both of the S and ORS in the Simulink. Don't forget, in coding we are using the closed loop transfer function. In Simulink you have to put open loop transfer function of these. See what I'm saying? Yes? Okay, so oh, this, hold on. Oh, okay. So this is S derivative. Oh, last slide. Okay. So that's it. So we are done with the body of the first order system. For next class, I'm going to start the second order systems. After that established. Yes. Let us try it. In some version, in the previous version of the MATLAB, if you put this zero, this, okay? You see that? You talk about it was giving see, it doesn't accept it. It says the time domain validation of current transfer for it doesn't accept, okay? So it says that it's not possible that the order of that is higher than the numerator. So that's why I'm putting the almost zero. See what I'm saying? Yes. 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 Yep. Okay. So well, let me, because I have to share this with you. I put this, no problem. Let me double check that. Oh, this is 3. Okay. There we go. Okay. Yep. Okay. So I'm done, guys. So see you next class. Okay. Have fun. Thank you.